Okay, so the first chemical reaction from the last set of slides was the precipitation reaction, and now we're going to talk about acid-base reactions, the second kind. All right, I'm sure you've heard of acids and bases. They're some of the most common electrolytes, most common and important electrolytes out there. Yeah, some things that they do is change colors with acid-base indicators. You've heard of them because there's a number of common household acids and bases. Hydrochloric acid is your stomach acid. Vinegar is acetic acid. Ammonia is a base. And acids, as you would imagine, are bases. Citric acid is in fruit. Acetylsalicylic acid, sorry about that, is aspirin. Anyway, here's some other. Okay, and there's just some nice pictures of all of our acids and bases out there. All right, well, we have a couple of different concepts when we talk about acids and bases. The original concept of an acid and a base was named by Arrhenius, and so it's sort of the simplest concept. And in the Arrhenius idea, an acid is something that, when dissolved in water, produces a hydrogen ion, an H plus ion. So, for example, nitric acid. Here in this equation, when nitric acid dissolves in water, the H plus breaks apart from the NO3 negative, and so we have produced an H plus ion. An Arrhenius base, then, is something that, when dissolved in water, produces hydroxide ions, or OH negative ions. So, for example, sodium hydroxide, when it dissolves in water, breaks apart to give us the sodium ion and the hydroxide ion. So, sodium hydroxide is a base. It's a little hard to see, for example, how ammonia then could be a base. It is a base, but how can we see it as a base? And the Arrhenius concept doesn't answer the question very well. It'll be better answered by the next one that we look at. But we can see here that when ammonia is put into water, what happens is the ammonia grabs the hydrogen from water to become NH4 plus, and then OH negative is produced. And so it is a base from the Arrhenius view because, again, hydroxide ion is produced. Okay, so the other concept is called the Bronsted-Lowry concept, named after two men who figured it out, who kind of created it. And in this case, an acid is really just the same thing. An acid okay, so a Bronsted-Lowry acid base reaction is one where an H plus ion is transferred from that acid to the base. So it's called a proton transfer reaction. So as I was starting to say, an acid is one that donates a proton. So that's pretty similar to the Arrhenius concept that we just saw. But here it's a little bit different because the H plus is donated to another species in the reaction. So there always has to be something that gets the H plus and something that gives the H plus. So the acid is the thing that gives the H plus, and then a base is the species, it could be a molecule or an ion, that accepts the H plus. Notice that sometimes when we're talking about acids and bases, we use the term proton. And literally, that's what an H plus is. And a hydrogen atom has one proton and one electron, no neutrons. And then if it were to give up its electron to become positive, it really is just a proton. So that's where we get the term proton transfer. It's really an H plus. So keep in mind for when we're talking acids and bases, proton and H plus mean the same thing. All right, so here's an example. If you, like we just saw a minute or two ago, ammonia and water to give us NH4 plus and OH negative. We see that ammonia is a base because it produces OH negative, but if we look at the Bronsted-Lowry concept, we can see that actually NH3 accepts to go from NH3 to NH4 plus. It has accepted an H plus, it's gained an H plus, and the H2O to go to OH negative has given up an H plus. So an H plus has transferred from the H2O to the NH3. So H2O will be the acid because it's the thing that donates the H plus, and NH3 is the base because it accepts the proton. Okay. A lot of times H plus really can't exist by itself. It's a really tiny little ion and doesn't usually hang out by itself. And so generally it associates itself with water to form an H3O plus ion, which is called the hydronium ion. Here's a equation of it. It's called the hydronium ion, and actually in reality even more than one water kind of surrounds the H plus. So it could be H3O plus, or it could be H5O2 plus. There could be a bunch of different waters surrounding that H plus. But anyway, keep this in mind, that an H plus and an H3O plus, when we're again talking acids and bases, either one kind of mean the same thing. And so sometimes chemists, when they're in a hurry, will just write H plus, but they really mean H3O plus. So if you see either one, they can interact. They could be each or the other one. All right, so now if we look more carefully at the HNO3 reaction that we saw earlier for the Arrhenius concept, in fact what's happening this time is the HNO3, if you look on the right hand side, becomes NO3 negative, so it's given up an H plus. The H2O has, to get to the right hand side, has gained an H plus, so there's been a proton transfer of the H plus from the HNO3 to the H2O. And so the HNO3 is the acid because it donates a proton, and H2O is a base because it accepts a proton. And then we have our products. So what you're probably noticing is usually before you get into this class you hear that water's neutral. Well, in this kind of reaction, in a Bronsted-Lowry idea, water can act like an acid or a base. It can have a different functions depending on what it's reacting with. All right, so they're very similar, these two concepts. The Arrhenius concept says that an acid is a proton donor, and it says that base is a hydroxide ion donor. The Bronsted-Lowry concept says basically the acid is a proton donor, but a base is a proton acceptor. And so really kind of the same thing, but the base is what's different. So for the most part, we will use the Bronsted-Lowry concept. So keep that one in mind. It's a little bit of a better explains things. Okay, well, you may have heard that there are such things as strong acids and weak acids. Bases, strong acids, weak acids, strong bases, weak bases. Now, it doesn't mean strong and weak in terms of concentration, like, weak tea or, ooh, that coffee's strong. More, it means it's a little bit of a different definition. A strong acid is an acid that ionizes completely when it's put in water. So, in other words, it's a strong electrolyte. It completely ionizes, it completely breaks apart into its ions. And so, HNO3 is a strong acid. When it's put into water, it becomes H3O plus and NO3 negative, 100%. Notice that the arrow is in one direction, and so we consider HNO3 a strong acid. HCl is another strong acid because it completely dissociates into the H plus or H3O plus and the Cl negative. On the next table, I list 6 common strong acids that you should remember: HClO4, perchloric acid. H2SO4 is sulfuric acid. HI is hydroiodic acid. HBr is hydrobromic acid. HCl, hydrochloric acid. And HNO3 is nitric acid. Also notice the same thing's true for bases. A strong base is one that completely ionizes. We haven't gotten to that slide yet, but I can't back up. So notice that there are also 6 strong bases that you should remember: lithium, sodium, potassium, calcium, strontium, and barium hydroxide. And another thing to keep in mind, that if it's not on this list, then it is not a strong acid or a strong base, depending on which category. So if it's an acid and it's not on this list, it'll be considered a weak acid. If it's a base and it's not on this list, it would be considered a weak base. Okay, so a weak acid then is an acid that only partially ionizes or partially dissociates. It's a weak electrolyte. HCN, hydrogen cyanide, is an example. Here's the reaction. And notice that we put a double arrow, meaning that only some, and it'll depend on the acid, and we get much more into this in second semester chemistry, but only a small percentage of the HCN will break apart into CN negative and H3O plus. And so it's considered a weak acid because it does not totally ionize. And the double arrows kind of indicate that. Okay, so continuing on, a strong base then, as we saw on the slide a little while ago, is a base that is entirely dissociates into ions. So it's considered a strong electrolyte. OH negative completely dissociates. So for example, sodium hydroxide breaks completely apart into sodium ions and hydroxide ions. If you look back on the chart a couple slides ago, you'll see that it's mostly the hydroxides of group 1A and 2A, except for beryllium and magnesium. So the 1A elements, lithium, sodium, potassium, and actually not listed on there, rubidium and cesium, are considered strong acids. Strong bases, but they're not on that list. Well, we won't run into them too much. But for the group 2A elements, it's basically calcium, strontium, and barium. And do notice that for the group 2A elements, when they break apart, notice that because there's 2 hydroxides for every barium, the hydroxide concentration is actually double that. That might be something that you need to know on a problem that you might come across. Okay, so then of course a weak base is one that's only partially ionized in water. A weak electrolyte, NH3 is an example of that, and like before, we see that we have a double arrow, so only a small percentage of the ions completely break apart. All right, so you need to be able to identify what acids are strong and what are weak. And just like when we did the precipitate reactions, if we have a strong acid or a strong base, because they're 100% ionized, we need to represent them that way, and so we write them as their separate ions. Weak acids and bases are generally represented as undissociated molecules when they're in an ionic equation, because such a small percent is actually ionized. So very similar to the precipitate reactions, where anything that was soluble we broke apart, anything that was insoluble we kept together. It's the same idea here. So two of the types of acid-base reactions that we'll look at. The first one, which is probably the most important one, is a neutralization reaction. Basically, an acid neutralizes a base, or a base neutralizes an acid. An acid and a base will react together to form an ionic compound, which we call a salt, and water will be the other product. So you can see here, yep, the ionic compound is called a salt. So if we look at this, HCN is an acid, KOH is a base, and like we saw earlier, you kind of swap partners, and this time though, because an acid always has an H plus and a base always has an OH negative, they combine to form water. So water is always one of the products of an acid-base reaction. And then the positive ion coming from the base, the K plus in this case, and the Cn negative, the negative ion from the acid, form a salt. And so an acid and base react together to give us a salt and water. And then the net ionic equation is always, always will have a transfer of a proton. All right, so let's look at the reaction of a strong acid, HCl, with a strong base, KOH. Okay, so HCl and KOH, you can see that the H and the OH again form water, and the K from the KOH and the Cl from the HCl will form a salt, KCl, which is, if you ever use salt substitute, it's salt substitute. So we know that HCl is a strong acid, so we write it separately as the ions. And we know that KOH is also a strong base, so we write that separately as an ion. And now going back to our solubility rules, we know that anything that has potassium in it is soluble, so our KCl is also aqueous, so we write that separate as their separate ions. H2O being a liquid, we leave as is. So now we can things that show up on both sides, the K plus and the Cl negative. And so the gist of our reaction, the essence of our reaction is that the H plus reacts with the OH negative to give us H2O, which is water. This is the main reaction here. If you have a weak acid or base, then your reaction will look a little bit different. So you can see in this case, if we have a weak acid, HCN, and a strong base, let's see, KOH, they're saying above, the KOH breaks apart into K plus and OH negative. KCN will be the product on the right hand. And since it's anything with potassium is soluble, that salt is soluble, so you'll have K plus and Cn negative, and then H2O. And so what's not shown on this slide is that the K plus shows up both on the left and the right, and they cancel out. So this is the essential reaction here. And we can't cancel anything else out because the HCN, being a weak acid, has to be stuck together in this equation. But we did cancel out the K plus that shows up on both sides. And so here's our the essence of our reaction. A proton has been transferred from HCN to OH negative. All right, so let's look at one more example. Write the molecular equation and the net ionic equation for the neutralization of sulfurous acid, H2SO3, with KOH, and it will produce potassium sulfite, K2SO3, and water. So here you can see the reaction, H2SO3, hydrogen sulfurous acid, and KOH. And although I've given you the product, you can see that you kind of have to swap the K and the H2. So the K goes with the SO3. Since SO3 is a -2, we need 2K, so K2SO3. And notice that K is only 1 with the OH because OH is a -1, but there's 2 Ks with the SO3 because SO3 is a -2. All right, and then we put the 1H from HSO3 over to with the hydroxide, and we get the water. Okay, so one thing you may notice is that this reaction is not balanced yet. So let's balance the equation. We need to put a 2 in front of the KOH, and then a 2 in front of the water, and that looks good. Okay, so now the next thing we want to do is identify which acids and bases are strong and if our salt is soluble or insoluble. So the H2SO3 is not one of our strong acids, and so we keep that together as intact H2SO3. But we do know from previous examples that KOH is a strong base, and so it completely dissociates. Don't forget that the 2 has to distribute, so there's 2 Ks and there's 2 OHs. K2SO3 is a salt made with K plus ions, and we know that according to our solubility rules, all potassium compounds are soluble. So we do know that the K2SO3 will break apart. And then we know that water as a liquid will stay together. Don't forget that the 2 has to come in front of the K plus because there's 2 Ks and 1 SO3. So now you can see it. The H2SO3 stays together, the 2K plus 2OH negative. And then on the right, we have 2K plus SO3 negative 2 plus H2O. All right, so on the next, we start with that. And then we can now cross cancel out anything that is a spectator. In this case, the only thing are the K plus ions. And so we have our net ionic equation. And just like the precipitation reactions, notice that the charges are the same on both sides. So even though it's not neutral on both sides, the charge is the same. There's a -2 on the right and 2 -1s, or -2 on the left. Okay, one other kind of reaction. Okay, so one other type of reaction, which is really not that different because it's still a neutralization reaction, but there's a couple of ions that are molecules or acids acids that are not stable in water, and so they actually form gas. So the first type are carbonates. If you react a carbonate, which acts like a base, with an acid, it will form carbonic acid, H2CO3, but carbonic acid is not stable. And so what happens here, so you can see here the Na2CO3, which is a carbonate, which acts as a base, reacts with 2 HCl. And then when we swap them, we see the Na and the Cl go together, and there's 2 of them to balance it. The other compound would be H2CO3. The H goes with the CO3, so H2CO3, which is carbonic acid. However, it's not very stable in water, and so it breaks apart into H2O and CO2. That's the acid that happens to be in your sodas. CO2, when it's dissolved in water, forms carbonic acid, and then if it's not very stable in water, it'll evaporate, or it'll move on out. The other one, you can see the arrow pointing up, just means gas forming. So like we had the arrow going down before, that was the precipitate forming. Anyway, the other reaction, which is also another acid-base neutralization, is when you have sulfites, SO3 negative 2. So for here, example, Na2SO3, the sulfite, sodium sulfite reacts with hydrochloric acid. Then actually what's formed is H2SO3, the acid, sulfurous acid, but sulfurous acid is not stable in water, and so it breaks apart into H2O and SO2. And SO2 is a very nasty smelling, that's your rotten egg gas smell. So hopefully you won't be playing with any of these. Okay, and that is acid-base reactions.